Welcome to solverfy.
On question 48, we are looking at critical temperatures and pressures of a series of compounds. And our compounds in this case are CCl3F, CCl2F2, CClF3, and CF4. In question A, we are asked to list the intermolecular forces that occur for each compound. So this compound, because there are two different elements with two different electronegativities bonded to carbon, this is going to be a polar molecule. So this will have dipole-dipole interactions. And as with all molecular compounds, this will also have London dispersion forces. The same is true for this molecule. Even though there's two of each, because of the structure of a tetrahedral, the polarities do not cancel, and this will be a polar molecule. So this will have dipole-dipoles and London dispersion forces. And again, with this guy, these will also have dipole-dipole as well as London dispersion forces. Finally, our CF4 is a non-polar molecule, so the only intermolecular force it's going to have are London dispersion forces. So that's question A. Question B asks us to arrange our substances in order of increasing intermolecular attraction from least to most. So what we're going to use here is the fact that the higher the critical temperature, the stronger the intermolecular forces. So we can basically list it from the lowest critical temperature to the highest critical temperature. So, and it also follows that the one with the only LDFs is the lowest critical temperature. So we're going to go from CF4 is our lowest, then CClF3, then CCl2F2, and then CCl3F. In question C, it asks us to predict the critical temperatures and pressure for CCl4 based on the trends in this table above, and then we're supposed to look it up and compare it. So for CCl4, we'd find that kind of here on our table. And if I'm looking at, I'll start with the critical temperature. If you kind of look at the trend, we can see that as the intermolecular forces increase, the critical temperature is increasing, and it's also because the molecular weight is also increasing, and therefore the critical temperature is increasing. And so we're looking at, there's an approximate difference of around 70 to 80, 85 maybe each time it goes up by a little bit more. So if I were to take the critical temperature for the one before it, for CCl3F, which was 471, and add, say, approximately 85, we would get a critical temperature of 556 Kelvin. And this compares, in the CRC, if you look it up, the critical temperature is actually 556.6 Kelvin. So this is pretty close. If we look at the critical pressure, again, the substance before it, CCl3F, has a critical pressure of 43.5 atmospheres. And we appear to be going up, kind of increasing, but it looks like it should go up by approximately 3 atmospheres following the trend. And so that would take it to 46.5 atmospheres. And the CRC actually says it's 44.6, so it doesn't go up quite as much as might be predicted by the trend, but we're still in the ballpark.